So good afternoon, everyone. Welcome to the fourth lecture of our very interesting introduction to Haskell and functional programming languages. I don't need to introduce the speakers again because you already met them 3 times. And I will give immediately the floor to Yorick. And Brink just joined us as well. Hello, Brink, good afternoon. And I think today Yorick will be the first speaker. So Yorick, if you would like to share your screen and start your presentation, you're most than welcome.
Great, thank you. All right, so hopefully that's workable. So I'll put the camera over to the side. I thought today, well, firstly, to issue a correction. Bertrand noticed last week that I omitted a word in the definition of the sieve of Eratosthenes. So if you did try to use that example, don't forget you have to sieve whatever's left over once you've removed all the non-prime numbers from your list. But today I thought we'd continue with the NewtonRaphson example. And we set it up last week as a stream. So we iterate the NewtonRaphson computation over an infinite list, basically, and then we only keep the part that we want. So because of the lazy computation, only the part that you need will be computed. And so one of the questions that was asked, what do you do if you don't know the derivative of your function? So here we had a polynomial, so that's easy to check that we get the roots. And we had a derivative, so that we can just calculate the NewtonRaphson method directly with that derivative. What do we do when we don't have that derivative? And so one option is to use a higher order function. So here I've defined approximate differentiation. What it does is just uses the usual formula for some small h, and we can apply that directly. So we had Newton applied to P dp starting at 0 to say an accuracy of so much. And that gives us an answer near 2. So instead of dp, maybe I can take the approximate derivative of p, say to accuracy, I'll just put in something random, and we can run it that way. So what's happening here is, again, because approximative takes a function and then an argument h, and then another argument x, if I only supply the first part by currying, it's going to create a function which takes x and maps x in this way. So that way we can work with any function provided we're happy with the approximate differentiation. The next step is perhaps maybe we don't want to deal with derivatives and we don't want to approximate either. So maybe there is a scheme that we can use to also do this kind of calculation without approximations. So I've created a data type here called autodiff. If I remember correctly, this whole story is called automatic differentiation. And the idea is a very simple one. We're going to do sort of algebraic operations, some composition with non-algebraic functions, but the main idea is that we have pairs of functions with their derivatives, and if we combine them in certain ways, we know what the new derivative should look like. So we create a new data type, autodiff, and it is, here's the constructor. The constructor takes a function and a second function, so that's the pair. And the first function would be interpreted as the actual function, and the second function here is the derivative of this first function. So the first thing we would like to do, well, we can work with this already, but it's no better than a pair. Maybe we would like to be able to add functions or multiply and then accordingly get the derivatives in those cases as well. But in order to do that, we have to, for example, if we look at the information for plus, if I have this correct, plus is defined in class num. So to add things, you have to create an instance of class num. And if we look at, I don't know if it will show me, let's see. Num doesn't tell me here, but I will get to that in a moment. To do num, And to be able to work with what we're going to output, we'll also need EQ and show. EQ meaning equal, when are things going to be equal, and to be able to show our functions. Well, the implementations in this case are going to be relatively easy because I don't know what to do for these. So if I want to compare two functions, I want to know if they are equal or not equal, I'm going to take the coward's way out and say they're never equal because I don't know how to compare them, because that would have to check all inputs to see if they are the same. So I'll make the equality false, and not equal is always true between two auto differentiation functions. And also to show, I also don't know how to show the function, so I'll just, again, take a coward's way out. I'll just show I've got an auto diff type of thing, and I won't do any more. So each time I want to extend the implementation, so override one of the built-in operations that are already in Haskell, I need to provide an instance. So this is an instance of EQ for equality. This is an instance of show to be able to create strings from our data and then to print it on the screen. And the last one is instance num, which is how we do the addition and subtraction and so on. Subtraction is automatic as long as we provide a negate. So let's see how we would do that. So plus, this is the section, in other words, autodiff A, dA plus autodiff B and dB. That will give us a new autodiff where the first argument is a function that takes A applied to X, and the second one is B applied to X. So that's pointwise. And in the same way, the derivative applies pointwise. And then we have times working in the same way using the product rule. So I've got the usual pointwise multiplication, and then the product rule or the Leibniz rule for differentiation. And then we need some extra things. So in order to subtract, we need negate. And that is simply to take the negative of whatever the function value is, so by linearity, and the same, the linearity for the derivative and the usual pointwise negation. We do have two sticky points, though, when we implement num. We also need abs and signum. So abs is not differentiable, so we've got a slight problem. We'll just pretend it's differentiable everywhere, and for the parts where it is differentiable, it will give the right results. So we simply take the absolute value of whatever the function is, and that will give us our new function, so the absolute value of the function at the point. And then the sign of the function value will be the derivative, and then applying the chain rule. So we'll get a little bit more into the chain rule in a moment. And there is no such, well, there is composition in Haskell, but we can't overload it. And then the sign, of course, will always differentiate to 0. And did I do this correct? Oops, this should be signum of the function value. And then there's one last thing that we need to do. For numbers, we always have to be able to convert from an integer. So for any given integer I, what we do is create the constant valued function I, and the derivative is constant valued in 0. And you'll notice I put here from integer I. I don't need to do that, but we'll use that in the next set of examples that we'll get to next week. So what does it say? Whatever I'm actually working with, so in this case doubles, take I and make it into a double. Is there anyone who does not know what double means? So I should just go back a step. Does anyone not know what double means? Double precision floating point. Okay.
No, nobody seems to complain.
Yeah, good. So that, because I don't know if I want to explain all of that. So that's good. All right. So what this is going to do is then provide a way to convert integers into doubles so that we can use it in our auto differentiation. So there's a couple of useful things that we might use in our examples. I haven't used it here, but I'll show how you can use it. The first is composition, which I've just called O, which is probably a very bad name, but it allows you to do this composition, F composed with G in this way. But notice it's not the dot, because I can't overload the dot. So it's a new symbol. And just to answer Sean's answer, there's 64 bits of memory. Double precision, yes, single precision is usually 32 bits, double precision is 64 bits, but it's floating point, which means the way that numbers are represented. In other words, that you have a mantissa and an exponent. So you have accuracy that depends on the magnitude of the answers in some sense in your calculation. So you can have a very large and very small answers, but if you're working with very small plus very large, you might forget the very small part because it only works in a certain region of the numbers. So like integers cannot represent fractional parts. Very large doubles cannot represent the fractional parts because they don't fit, but very small doubles can. So it has a range of values that it can store. But anyway, that's perhaps, no, thank you, Sean. Thank you for the input. All right, so this is how we compose. It's the usual chain rule. Here is composition of functions. So b at a point x, we apply b to x and then a to that. And then the usual chain rule, calculate b of x, apply the derivative and multiply with the derivative of b at x. So the last couple of things is just examples. In the examples, we will also, well, not yet, but just now I will use accessor functions. An accessor function is a way of getting the information out of this autodiff. So I've chosen to call it f and df. F takes the first part and df takes the second part, in other words, the derivative. All right, so why do we want to go to all this trouble? I've given some examples here. So to auto-differentiate exponentials, it would just be the exponential twice. Sine is the sine and cosine in the usual way, and we can use composition on this level to create the derivative of the cosine. And then we can create a function such as exp prime, so a new version of exp. And I should explain also why I've chosen to do this, and this is to get out of a mess. But what we've done here is we create the auto exponential, and then we compose it with whatever the auto differentiation or auto derivative a that we have there. If we look up exponential, I think we'll see it here. Exponential is part of fractional, and with this we generally have a whole lot of extra things that we have to implement. And I'm lazy, so I'll leave it as an exercise if you want to look at these things, but I didn't want to go into all the transcendental functions. But here's the real advantage, I think. So we can create a function x, which is simply the notion of an indeterminate, which given a point gives us exactly that point back and has derivative 1. And from this, we can construct a function g, which is the product of x minus 2 times x minus 3. And so this is interesting. I've composed x minus 2, and I never defined how to subtract integers from auto derivatives or auto differentiation instances. But it's automatic because I have from integer. So Haskell knows how to convert this. It must be from integer first and then combine it in the usual way. So now I've got g. Of course, if I load day, which one are we on? 3. Oh, this was 4. Then we've got g. Of course, I can't see it, but I can say what is the f part of g applied to 2. And that would be just 0 from 2 minus 2 times 2 minus 3. That's where the minus is coming on from, is the 2 minus 3 and the imprecision in the calculation. I can also ask what is the derivative of g at 2, and it will give me minus 1. So let's compare with this with the original example. Did I load it? Oh, it's dp, my mistake. So dp at 2, which is minus 1. So it gives us the same result, but I can work purely algebraically and keep track of the derivative in the second argument of the pair. And we'll notice here one of the particular things that I did, firstly, the brackets to isolate the type. So this is type double to double, not double to double to double to double. So it's not concatenation or composition of these two functions. So I need the brackets. And well, at this stage, I assumed I need double, but that's not true. So maybe in the next lecture, we can convert it to something else and then see how it would work in a more general setting. So the last thing we can do is convert our Newton method to one which takes an autoderivative or autodifferentiation. It takes an autodiff FDF and an initial point x0 and an accuracy epsilon, and we just take that f by pattern matching. We can pull out the f and the df and calculate this way. So let's try that. That would be Newton AD, and I've got g is my autoderivative. And let's say we start at 0 again, and accuracy, so on, and we'll get the answer in that way. Of course, I could also do the normal Newton and take the f part of g, if I can spell, and the df part of g, and initial point 0, and accuracy, and then I would get to the answer. All right, so I think I'll just pause there for any questions, if there are any. We didn't try any of this composition, so maybe I should show you that. Let's see what G composed with G looks like. So now I can take f of G and apply it to 2. I don't remember what it's supposed to, of course that should be 0 because it's G composed with G evaluated at 2, which will be a 0. And that we'll have to check, but if I remember correctly, that should, not G, H. No wonder I'm getting lost. Aha, there we go. So H at 2, and is that right? G at 2, and then we can take also derivatives at H. Except that I still can't spell, so let's try again. There we go. So that then allows us to do this algebraic construction. We can also use exponential signs and cosines and build up our expressions without worrying about the derivatives.
Sorry,
yes, Keegan. Sorry, who's speaking?
It's Ilya speaking. Sorry, there is a question from Zurab in the Q&A, which is stepping back. What are we trying to achieve with autodiff? Can you please?
Okay. So there are 2 reasons I'm looking at this. The first is to look at a new data type. So I'm creating a data type which can track differentiation for me. The second is that differentiation, because, well, at least with these functions that we're working with, exponential signs and cosines, we know how to combine derivatives so that we don't need to create a derivative function for every function that we might work with. We can just create a derivative for some simple cases, and then by composition, create functions and their derivatives for any problem where we would need a derivative. I'm not sure if that answers the question well enough.
I don't know either, but Zurab might comment.
Yes.
Yeah. She's asking for example. Can you give an example why it could be interesting and important?
Right. So it's basically what I've done here is a very simple example. So if I've got G defined this way, but I can do it with a very complicated function. You might argue you can create the function also in Mathematica, but I suppose the argument here is that it's already built in. So once I know how to work with these variables, I can create arbitrarily complex expressions for any function I like, and the derivative is already included. Why would you like to do that? That's only with problems where the differentiation, firstly, numerically doesn't cause problems, because that could happen if you have a, say, very large expression and you're composing in all these steps, that your numerical calculation might become a bit imprecise. But ignoring that, it allows me to not think about differentiation because Haskell can think about it for me. And an example where I would do this kind of thing is, so whenever I have numerical methods or say differential equations or differential operators applying to some problem, then I can build into the algebra how to work with these kinds of problems. So this is sort of more leaning towards computer algebra. So Sean asked if there's any comma operators to separate concerns like in C#. I don't understand what that means. Sean, would you mind giving an example? Unless Brink knows.
You can also quickly give Sean the right to speak to make it easier.
Yes, that would be great if Sean is willing.
Sean is welcome to talk, yeah, and ask.
I do apologize. I'm actually at work. Thank you very much. Look, I'm a C# developer, but I'd like to find out after every function, for argument's sake, auto exponential, auto sine, and auto cos. Usually most languages have a comma delimiter at the end to separate the concerns. Is there any such function in Haskell by any chance?
So can you explain what separate concerns means?
So if you put a comma right after exponent, and a comma after cos, yeah, and a comma after cos, and a comma after sine, that separates the concerns of the three functions that you can call, basically.
Oh, I see. So I don't know, Brink, do you perhaps know if there's some analogy? I don't think.
So the whole thing is Haskell goes with the philosophy of as much white space as possible. So the new line is already saying, well, it's separate concerns. There's no reason to have a comma there. Why? That's what the new line is doing.
So you can do it with semicolons, right?
You can do it with semicolons, but yeah, people will sort of frown at if you write your Haskell like that. So yeah, you can put a semicolon, but the new line is already doing it. So since white space is sort of important, yeah. So similar to, I think even more than Python, so sort of white space plays a role, and it's got the philosophy, why type something if anyway by white space you'll do it to make it more readable, so you rather just build that into the language.
Yes. I suppose what you'll find, Sean, is there is a canonical style, which is not this way, but you could do it with semicolon. I'm supposing at this point that that's answering the question. And if you could just mention. Okay, great. And then I don't know if I saw any writer. So Zurab is much sharper than I am as usual. Okay, so Zurab says, we're creating a system where we input derivatives as axioms and derive other derivatives from them. And the second comment, I guess, is a thank you, Zurab, is actually to explain it, to fix it. Where we input derivatives of specific functions as axioms, yes, and derive other derivatives from them. And as you said, basically how one teaches calculus usually. That's right. I mean, it's obviously not going to solve every problem, but it certainly makes the problems of these kinds a lot easier to deal with. Keegan, yes, this is a kind of recursive differentiation. So where you basically have a language of differentiation and you reduce what does it mean at the top level, the differentiation, and then you can see if your language has plus, then the reduction is to have the addition of the two derivatives, and so you keep reducing down until you cannot any further. And cannot any further is what Zurab was speaking about as axioms. Great. Okay, so I think we're almost out of time, so I'll maybe just have a teaser. What we can do next time is we'll look at polynomial over an arbitrary type. Well, it will be a numeric type, so polynomials over rings or polynomials over integers or double or something like that, and see how we can do calculations with polynomials. And at this point, I think, yes, I think we can formalize a differential ring. I haven't written it, but if you like, what we can do is we can maybe prepare it as part of the examples for next week. So that would be a similar idea, right? So you have a pair, you've got your underlying ring and your derivation. Is that what you mean? And then the rules will be more or less the same, except that we're going to run into some trouble with the idea of negation, absolute value, and signum. But what we can do is just put something in that doesn't really matter in those cases, as long as we have some 0 point or something like that. Great. Okay, so maybe we can look at that next week. We can add, and what we can do is that was actually in the plan. Is we'll take this and we'll take it away from double and actually put it over an arbitrary type, well, a numeric type, so that we can actually do the calculations. All right, so Brink, I don't know if I went long enough. Would you like me to do a little bit more, or do you want to take over with a bit more of the language structure?
It's 100% your call. So if you feel like going on next time, I don't mind starting, but yeah, it's up to you.
Let's try to do it here, and then next time I'll do polynomials. So we've seen auto differentiation. So the changes for the differential ring will be relatively straightforward, I think, except to formalize the ring. So I'll just have to add some examples, or we'll use the obvious ones. And yeah, then we should be able to do that quite easily, and then just do some examples with polynomials. So I think we'll have enough time if that's okay. And then, but we can always at the end jump in a little bit if there's a lot of extra time.
Sounds good.
Great, thank you.
Yeah, thank you very much, Yorick.
Okay, so I'll start where I left off last time, and again, it was just me that said nothing, so hopefully you can hear me now. All good, everyone can hear,
yes, we can hear you clearly. Thank you very much, Brink.
Perfect, thank you. So let's start where I left off last time, and that's with Zurab's favorite maybe type. So the whole idea is to, so instead of rolling my own maybe, and since I did it last time, so the whole idea is here to use the maybe type and give some motivation. So essentially the way, so sort of defining your own types. So the A is a type variable. So this pipe here, you can think of it as a disjoint union. And the A, you could make maybe ints or maybe strings or maybe doubles. So that's just a type that you'll specify. And so either it's nothing or it's just of whatever, say just of an integer. So the way you make the maybe type is it's a disjoint union of either nothing or say just of some integer. And you can think of the way you construct your types as you can use base types that's already defined, and you can use these constructors, which are essentially functions. So say the A is an integer, then I could have here on the right hand side just 5 or just 7. So it takes the integer 7 and map it to just 7, which is then a new instance of my maybe type. So let's just use this maybe type in some sample code. And so let's, and maybe some of you have seen this kind of example. let's implement our own safediff. So what we want safediff to do, we just want to do integer division, and what we want to do is it should take an int, so it should take 2 ints, and if the second int is 0, then we should map to nothing. So instead of returning an int when we do integer division, let's rather return maybe of int. So there's the type signature. So what we do is save diff, we give it the 2 integers x and y. And so now the question is, there are sort of various ways to implement it. So let's use, say, a if statement. You can also do pattern matching or other ways as well. So if what we want to do is we check if y is not equal to 0. It's not equal to 0. Then what we want to do is we simply want to do x or diff. Well, let me write it in prefix notation. Then we simply divide x and y. So let me just, so for example, if you take diff of 10 and 4, you'll just get 2 back. So you do integer division. So if y is not 0, we just do diff of x and y. Else we get nothing. You see why it's unhappy. Okay, these parentheses aren't necessary, so I can just remove those. Okay, and I guess here as well. So it's more a matter of style than anything else. So let's now try it out. So let me just make sure I've loaded main.hs. Oh, okay. Yes. So obviously this, yeah. So if I can do the actual division, I should return just of the answer that I get. So that should be just of diff. Else nothing. So let's try again. Now it's happy. So let's do, say, save diff of, say, again 10 and 4, and we get just 2. But now if we do go save diff of 10 and 0, we'll end up with nothing. So this is sort of what I've mentioned last time, sort of a nice use case for this maybe type to sort of capture when something goes wrong with the computation. Instead of throwing some exception, you go the nothing route. Otherwise, you keep going with the just route. So if everything is fine with the computation, you just stick within this just part. So you wrap everything that you would have done in a just. But if there's any error condition, then you go into nothing. So now that we have that, let's make a new type, an expression type. And you can think of these as, I'll keep it as simple as possible. Think of these as maybe you have some expression with various operators in, and you've already parsed it, and you have some sort of parse tree, which I'll just represent by a data type, and then you want to evaluate the expression. So what the expression could be, it's just val of some int, or so this pipe is or you can think of it as disjoint union. So essentially, the left part of this expression type is an int, but I just stick a val in front of it to distinguish it from normal int. So val int, so expression could be, say, val of 10, or we want to do division of a left expression and a right expression. And just so that we have a 2-string method, let's do deriving show instead of implementing it ourselves. So just so that we have expressions to play with, say we could have, say, one expression could be, say, diff of val of 10 and val of 4. Maybe this is my one expression. Let's make another one. Say diff of, again, val of 10 and maybe val of 0. Okay, so I have essentially expression type. So now I can print this expression. And so an obvious exercise would be to sort of make this expression data type a little bit more realistic at, say, addition, subtraction, exponentiation, whatever. So we have at the moment just diff and constant values. So now what we want to do is we want to evaluate an expression. So we want to write the eval function. And what it should do is it should take an expression. And now the problem is you could potentially have division by 0. So you want to get an expression, but sometimes you might not get an int if you evaluate an expression. So this expression type is sort of representing the parse tree of your expression. So really what we want is maybe of int. So let's see if we can implement this eval function. Now we want to do pattern matching. So this expression type, it's either this or this. So we just do pattern matching on the two options. So the first one, if it's just value of some integer n, the way that we do it is, well, we say this is just n. So remember, since we go to maybe int, it's either nothing or it's just of the integer value. And now for the fun part. And what I want to use, and this time just explain it on the high level, if we get info from the maybe type that I'm using here, we'll see it's a monad. So without explaining straight away all the details, I want to show you the advantage of making use of a monad. And I've sort of just stolen somebody else's example, which is sort of the easiest way to show how handy it is to use monads. And I'm going to, behind the scenes, I'm essentially going to use what do you what's called in category theory, right? Kleisky composition, right? Do I pronounce it the right way, Yorick?
I think it's Kleisly, but yes, that's
Kleisly
yeah.
composition. So,
yeah.
so I want to use the Kleisly operator, but let me first write it. Haskell has some syntactic sugar, so that you can write it. It's essentially covering up the fact that I'm using this Kleisly composition. And so what you can do is you can look at the type of, so essentially what we have is we have this Kleisly composition defined for the maybe type. So if you look at its type, so maybe, so M must be a monad. So in our case, the monad would be maybe int. So you have the monad value, you have this function with which you'll compose it. A goes to some monad of B. So in our case, A and B will just be ints. So A and B are type variables. We'll just take it as int. So it will go, we'll take a maybe int, compose it with some function that goes from int to maybe int, and the answer that you get is maybe int. So that's what I want to use now. So the whole way we use it, so eval of diff of a left and a right sub expression. Now, remember, this is a recursive definition for this expression type. So this expression here could be val of an int, but it could be another diff. And that expression could be another diff, and so on. And I'll use what's called the do notation. And this do notation, it's just putting syntactic sugar over the slightly composition operator. So you can use the do whenever you make use of a type, which is a monad. So in my case, the monad is really the maybe int. So what we do, and here you'll see some new syntax. What I do is recursively, I evaluate x. So I evaluate that expression. So that expression, I just evaluate it. And here you see new notation. And the way you should think of it, so when I do this evaluation, I'm just, there's two options. Since here's the type, it's either just a 5 or just a 10 or whatever, just of some integer value, or it's nothing. Now, the way this slicely bind is defined for the maybe type. So if it's an integer value, I essentially take that integer value out. So let me just to make it more readable, let's call that left and right. So if I evaluate the left side, let's assign that to x. You can think of, well, if I evaluate and it evaluate to nothing, then essentially I don't have an x. But the closely bind will sort of handle that error branch of the whole computation. And why? So there we just do eval right. And now what we can do is, so for the moment, think there wasn't a division by 0. So say the x and y turned out to be just of some integers. What I can do, so you can now think of, well, that eval is a just of integer, but the x and y, you can think of it simply as integers. So now I can say, well, safe, what I want to return is safe diff of x and y. So let's see if this worked. And we have some test expressions here at the top. So if I do, let's see, eval of e, we get just of 2. But if I do eval of e prime, I get nothing.
Then can I just highlight a question from Sean? He said, it would be nice to implement a catch statement and have a note added to a repository should an error occur like division by 0. And I think this you could address here already in a way.
So let me just, so if you, so maybe I can do an example like that, or let me do it maybe here. So there's another type, which is also a monad called the either type. And the way the either type is essentially the maybe type on steroids. So instead of just having one type variable, you have 2 type variables. So you have a left and a right. So the just part is replaced by the right part. So in our case, it would be right of int, and you'll log your errors in left of string. So if you want to log where the error happened, what the error was, you'll use this either type. So yeah, so it could be a nice exercise to take this very simplistic example and replace the maybe type by the either type, and then log what the error was and where it happened.
would it be correct to say that the do notation is sort of doing what you would do with a try catch block anyway, meaning try some things and get the error at the end, whereas your error here would be nothing, so maybe it doesn't tell you anything, but in principle you would.
The whole idea with using, say in this case, monads, and more specifically either, or in our case the maybe type, if you look at the try catch blocks and so on, from a purist point of view, it's really ugly code that you have to write, and sort of you try and avoid that. And so the try catch block, that's actually all hidden in how you do this Gleisli composition.
Right, in the type.
In the type, so it's, yes. It's really, so let's just to make it a bit more concrete, since I have a few minutes, instead of starting with something completely new, let's see if I can rewrite this eval of mine, and let me use this bind operator instead of this do notation, which is just syntactic sugar. So I'm just going to copy and paste that, and wherever I have eval, I'll just replace it with eval prime. And now I don't want to use the do notation. So what I do is I evaluate left. And then I use the bind operator. So you can look at the type of this bind operator. So this is what you should keep in mind. So I now want to use this bind operator that's sort of just covered by syntactic sugar, the do notation. And in fact, if you say write Java code and you use something called the flat map there, which is doing the same thing, you don't have this nice do notation, and you'll write code that's very similar to what I'll attempt to write now. So I eval the left. So eval left, it's either nothing or just some integer. And then I have to write the lambda function. So the way you should think of this lambda function, so the x, it's in essence representing, if everything went well and it was just a 5, that represents the 5. But yeah, if it's nothing, the bind operator takes into account that x, well, it's you can't really find it. And then what we now write this lambda function here. So then next we do eval write. And you'll sort of see why the do notation is a lot more fun to write. So we've evaluated left and say it went well, and x is say 10 or 5, where you got just of some integer. Then you have to evaluate right. And the whole complicated part here is you have nested inside this lambda function, you have another Gleisli bind. And I think now I can just do my save diff. Let's just see, I think it's happy, but it just, okay, obviously I forgot to prime everything. Let's see.
Is it also line 17?
17, yeah, true there as well. Yeah, all is good. It's just the linter is telling me don't write code that rather not do this, rather use do notation. That's what the linter is complaining about. So now I can do eval prime of, say, my expression E. Sorry, there we go. It was just stuck there for a moment. And again, so recall here was our E. And yeah, so we get again 2. So, and we can also do it on E prime. So essentially this nice do notation, and which is using the fact that the maybe type is a monad. So you have the bind. So typically you'll write it with the do notation instead of using try catch blocks. And if you really want to see what's going on behind the scenes, this really gets translated into this code here with the eval prime. Okay, so let me see. Any questions on that? Otherwise, if there's no questions, we can maybe use, let's make some more types. So let's make our own list type just to get some experience in writing our own types. So let's make our own list type. So that I don't type too much, I'm just going to call it L instead of list. So data list A. So what is a list? So, well, either it's an empty list. So E just represents the empty list. Then the pipe is disjoint union. And then we have a cons operator. Now, what's cons doing? So it's going to concatenate the head of the list with an LFA. And instead of implementing our own toString method, let's just derive show. So let's see how that works. So now, so you can say have X, or let's make it L as some list. Okay, for some reason. Oh, there we go. So we can do a cons of maybe the head of the list is 10. And then maybe we cons 5 with the empty list. Okay. Apologies, well, it gives you time to catch up. My laptop and Zoom seems not to be friends, and every now and then it gets stuck here. And so let's print out L. So now we see we have this list. We've made our own list, but see, this is not a lot of fun to sort of yeah, it doesn't look that nice. And I guess part of the problem is we use this C operator in prefix notation. And so in lists, typically, well, you have the cons, which is just that. So let's try and do something similar. So let's let me use 2 more minutes, and let's just define. So again, let's do list of A. And now instead of the cons, let me show you guys. So I want to define an infix operator, which will be my list cons operator. And just so that we don't have a clash with, so with this notation, I'm simply saying this operator of mine, it's going to fulfill the same role as the cons, the C, but I'm going to use it in infix. And the 5 is just a weight that I give to how strong it should bind. So it's not going to bind as strong as, say, plus or something. So, for example, if you get some info about plus, you see it's infix left. So the left is left associative. I'm going to make this operator of mine right associative. And plus binds with a strength of 6. This cons operator of mine will bind with a strength of 5. So it's the binding is gonna be weaker than the binding for plus. So the way a list should look like, it's either empty or pipe disjoint union. what we want is it's in type A. And then I guess list of A. Let's see, it's unhappy. I might have to look at my cheat notes here. Anyone can spot my error here? Infix. Data list A, so it's an empty list, or it's the element A. Okay. Not often I get stuck, but I guess this time I got stuck. Let's see. Let me just look here at my own crypt notes here somewhere, hopefully. Data list A. Oh, okay. I'm still confused where the issue might be.
Does it load all right?
Oh, valid point. Let's see.
Data with a capital D. Yeah, sorry.
Yeah, I'm not quite awake there. Yeah, thanks. Okay, so now
may I interject a question quickly? Since I haven't seen this part before. The operator that you introduced, you're using it at the type level, but I guess you could use it also at the function level. So you could use the same symbol in different ways. Is that right?
Yeah, so yeah, I follow your question. So, there I can sort of just point out something that's a little hazy in my head as well. So when you make a new type, so let's look, say, at this expression type. The way you do it is you use essentially functions and current types you already have. But you can see that function is treated slightly different. Obviously, it's some sort of constructor, but it sort of wants me to write the constructor function with a capital letter.
Yes.
So in a sense, it is a function, but it treats it, the compiler treats it slightly different.
And Zurab was asking about this, meaning that it is a function, but it's also different because the compiler handles it a bit differently.
Yeah, so since if it was just a normal function, I would not, so with this E and here where I didn't use the infix, I would not be allowed to write it with a capital letter, since the Haskell compiler will say, well, what is that? I don't understand, it's a capital letter, so it can't be a function. So it is a function, but sort of the compiler treats it as a function that I use as a constructor to construct my actual values.
Right.
And
thanks.
I can, for example, here say, well, what is the type of E? Well, I guess I need to sort of reload and say, well, what is the type of E? And it will say, E is essentially a function taking no arguments, and it gives me a list of A back. And I guess it will also, so here I'm just, instead of having this constructor function, I'm just using it in Infix notation. So let's hopefully this works out, since this would be a good place to stop. Yeah, so here you can see this. Yeah, I just want to use it in Infix, since it's nicer to sort of do sort of an Infix function constructor also. Then its toString is going to look nicer. It's something that takes a value of type A in a list and give me a new list. So it takes a list of A, and it gives me a new list. So that's what that function is doing. And yeah, I said I'll use that function in Infix, and I'll make it right associative. So also a good homework exercise. See if you, given this definition, and I'll stop here, see if you can make it into a functor. So that's maybe a nice little exercise, just turning this list now into a functor so that you can map over this list. And a little bit more hardcore, last thing I'll say, and then I'll stop. See if you can make it, okay, this is more difficult, see if you can make it foldable. So now that we have this list that's defined here, see if you can make it foldable so that I can do left and right folds in it, just like the normal list. So yeah, so thanks everyone. Yeah, so let's stop here.
Yeah, thank you very much, Brink and Yorick, for another very interesting lecture. We had already several questions. I'm not sure if there are more that might come at the last minute. Maybe let's wait a second to see if
perfect.
If our
Keegan was sharper than both of us and
sorry
the data. Keegan was sharper than both of us and spotted data.
Yeah, no, some participants are wide awake.
He might have to be upgraded so that he's also presented, so that he can interrupt us with doing it in a vocal way and say, you guys are asleep, or Brink, you asleep.
Yeah, yeah. There is a more generic question by Sean that you might want to address. Where is Haskell used mostly?
Well, so you see it, there's some, nowadays some of the cryptocurrencies went the Haskell route for the smart contract languages. And in various of the big companies like Facebook and so on, they have actually Haskell teams. So, and concurrent code is it's quite used widely. So there's a library called Haskell developed by Facebook, which is a Haskell library to write various kinds of concurrent code. So I agree. So if you look at the popularity, I think it's more or less ranked 30th. But from my point of view, as somebody at the university, why I like it and I like to teach it. So obviously, I can go for a language like Scala, since Scala is a big language at say Amazon and Cape Town. I know all our students write Scala code there. If you look at a lot of the big research projects anywhere in my field, I see a lot of them being developed in Scala. The problem is if I let the students use Scala, it's just mixing two paradigms, both object-oriented programming and functional. So in my opinion, Haskell is sort of a nice stepping stone if you really want to go in and use Scala eventually, just to get to grips with the functional aspects before you start mixing functional with object orientation and sort of you in the modern day version of C++.
Thank you. Hope that Sean is satisfied with the answer. Yes, Sean, thanks. I don't see at the moment any more questions, but maybe we can, if people need maybe a minute or two to come up with something, we can discuss them on the other side, in Kumo space. If Yorick and Brink have a few minutes to spare, maybe to interact in a less formal and structured environment.
Perfect, thanks, Francisco.
With some of our participants. Yeah. Then maybe
there's one last question. Should we address it quickly from Alfred?
Sorry. I didn't see it. No. Yes. Please. Sorry, I missed it. Yeah, please.
Yes. So that's actually another reason why I became interested in it, since with many papers that I was reading, sort of on the theory side, instead of giving pseudocode, people were sort of using Haskell, especially in more the theory side. They were writing Haskell code instead of pseudocode. And I sort of saw it sort of with automata theory. There's something called derivatives. And so once I sort of started reading all these papers that made use of derivatives of words and so on, all of them were implementing their libraries that sort of illustrated the value of the theory and where it can be used and how it can be used in Haskell. So one can sort of understand it, since it's mostly pure functions that you're interested in, not that many side effects. So sort of more on the theory side with, say, the automata theory libraries and so on. Yeah, Haskell's definitely popular there.
Excellent. No, thank you very much. And maybe before we leave for Kumo Space, just a reminder that November has 5 weeks. So we will be back next Tuesday for one more lecture. Sorry, I think I might confuse you because last week I made a comment about maybe adding one more lecture, but we have it automatically. It's a kind of auto diff of number of lectures. Yeah. Okay, so no, thank you very much, Yorick and Brink again. It was again very, very interesting and informative and motivating to learn more. Yeah. So a good afternoon to those of you that might not be able to join us for a few more minutes in Kumo Space. Otherwise, we will chat to the others just now. Thank you very much. Have a good afternoon.
Thank you, Francisco.
Thank you.
Thanks, Yorick.
Thanks.